All right, today we're going to learn how to write Lewis structures. All right, so this is very important. All right, so we're going to start with water. All right, and when you have water, you have to count your number of valence electrons. All right, H is in column 1, group 1. All right, so that has 1 valence electron. So 2 hydrogens, 2 valence electrons. Oxygen is in column 6. It has 6 valence electrons. All right, and so your total valence electrons is 8 for water. When you then write the skeletal structure, so that's number 1, we found our valence electrons. The skeletal structure, all right, you're going to have your central atom is going to be the first non-hydrogen atom. So the central atom is the first non-hydrogen atom. All right, so H is never a central atom. H always has 1 bond. All right, and so your central atom here is O, and that O is bonded to 2 H's. All right, so that is your skeletal structure for water. All right, so now when we put in 2 bonds, you have to know that a bond is 2 electrons. So we took our 8 valence electrons, we added 2 bonds. And so now we have our 8 valence electrons, but minus 4 for the 2 bonds. So now we have 4 electrons left. So now we have to distribute the remaining electrons in order for all of our atoms to have an octet, except for hydrogen. Hydrogen, always 1 bond. Never put an electron pair on hydrogen. Hydrogen is always 1 bond. All right, so 1 bond to hydrogen, that's exactly what you want. All right, so the 4 electrons, 1, 2, 3, 4. All right, and so you have now an octet for your oxygen, and you have your 1 bond for your hydrogens. All right, so if I went with 5 here, because there is another possibility, all right, so we used up all 4 electrons and it worked out perfect. Sometimes we are not going to have enough electrons. If there are not enough electrons to give all atoms an octet, you're going to have to add a double bond. Add a double bond. And a double bond is then going to be called a pi bond. All right. You're going to add a pi bond for every 2 electrons short. All right, so if it was you needed 16 and you only had 14, you add 1 bond. If you needed 18 and you only had 14, then you would have to add 2 bonds. For every 2 electrons short, you have to add a pi bond. The other choice, you can put that as like 5A and 5B. If there's too many electrons, you put the extra electrons on the central atom. All right, so it's a lot easier when there's too many. You just put the extra ones on your central atom. All right, now when you're doing hydrogen, so hydrogen is in row 1. Again, row 1 just has the 1s2. So H always has 1 bond. In the second row, we have the 2s and we have the 2p. And so when we have this, we have our octet, 8 here, duet, 2. All right, and so when you have your octet, nitrogen, oxygen, and fluorine, these 3 must have an octet. All right, so they have to have 8. Now, when you have your carbon, your boron, your beryllium, and your lithium, these can have less than 8. So they can have less than 8 electrons. N, O, and F in every single molecule. They must have an octet. Your lithium will never have an octet. It'll always be less. Beryllium, again, if it has an octet, it's going to have a lot of charges. Boron usually doesn't have an octet. Now, carbon normally does have an octet. It doesn't have to have an octet, but it normally has an octet. But nitrogen, oxygen, fluorine, if they do not have an octet, you have the wrong structure. They must have 8 electrons. Every single structure that has an N, an O, and an F in it, they must have an octet. None of these can have more than 8. None. Maximum is 8. All right, so when you have the 1s2, hydrogen, max is 2. That's why there's one bond and only one bond. Your max here is 2. For the second row, which is your lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, the maximum number of electrons is 8. If you ever have more than 8, it is 100% wrong. All right, so we were doing these last time. All right, so again, you find your periodic table. You see that N is in group 5, 5 valence electrons for N. Hydrogens in group 1, 1 valence electron. We have 2 of them. We find oxygen, group 6, 6 valence electrons. Hydrogen, 1 valence electron. We simply add up our numbers and we get 14 valence electrons. When it is written this way, when it's written as NH2 and OH, that means that the N is bonded to 2 H's and this O, which is bonded to this H. It is not NH3O, it's not NOCH3. When they write it this way, the skeletal structure is N bonded to an H, bonded to an H, bonded to an O, but this O is the one that's bonded to the H. All right, so when they write it this way, it's not written as NH3O. That would be, you'd have to do something different with that. When they write it as NH2OH, that means that the NH2 is together, the OH is together, and that O is bonded to the N. All right, in order to do this, we had to put in 1, 2, 3, 4 bonds. So we have to subtract 8 for the 4 bonds, because each bond is 2 electrons. And so we are left with 6. And so hydrogen, 1 bond, all 3 hydrogens are exactly how they need to be. Nitrogen and oxygen must have an octet. So there's 2, 4, 6 on this O, an N, it needs an electron pair. So we try to write an electron pair, except it won't let me. All right, so you put in your electron pair. And I'm just going to put a line and a line and a line. Note that a line is equal to an electron pair. Since this computer does not want me to write dots and it changes things. All right, so many times you'll see it that way. A line is indicating a lone pair. So if you see a line, that indicates a lone pair. All right, and so 6 was the perfect number. And so there is your Lewis structure for NH2OH. And then they go through all the different steps to do that. All right. So when we go to CO2, all right, so that's column 4. So carbon's in column 4. Oxygen's in column 6. We have 2 of them. That's 12. So our total is 16 valence electron. All right, so carbon is our central atom, bonded to an O, bonded to an O. So we subtract 4 because we put in 2 bonds. And so we have 12 electrons. We try to give everything an octet. 2, 4, 6, 8, 10, 12, 14, 16. We need 16 electrons. We only have 12. We are 4 short. All right, so that means we have to add 2 pi bonds. 2 double bonds. All right, so we have then our carbon, and now we have to have a double bond to O and a double bond to O. All right, so this was the 2 single bonds, which are sigma. All right, so a single bond is sigma. So that uses the s orbital, sigma s. All right, so the pi bond, that uses the p orbital. So pi bond, p orbital, sigma bond, s orbital. All right, and so now we have our 2 sigma bonds. Now we have also our 2 pi bonds. So now we only have 8 electrons, and that is the perfect number to give all of them an octet. So carbon already has 4 bonds. That's an octet. Oxygen needs 4 on this side and 4 on that side. So this is your Lewis structure of CO2. Remember that the line indicates a pair of electrons. All right, that is not a bond. That is a pair of electrons that the computer here doesn't like me to write. All right, if we do HCN, all right, so the central atom is never H. So the central atom is carbon. All right, so the carbon is bonded to a nitrogen and it's bonded to a hydrogen. All right, so when we do this, we have 1 plus 4 plus 5 equals 10. Column 1, group 1, group 4, group 5. That's our valence electrons. We put in our 2 bonds. We subtract 4. 6 electrons remaining. We need 1, 2, 3, 4. 1, 2, 3, 4, 5, 6. Yeah, okay, 5 lone pairs, which is 10 electrons. We need 10 electrons. 2, 4, 6, 8, 10. We have 6 electrons. Again, we are 4 short. Now we cannot put a double bond to hydrogen. This has to always remain as 1 bond to carbon. If that ever changes, it is 100% of the time incorrect. And so you cannot put a pi bond between a carbon and a hydrogen. Hydrogen always has 1 bond. But we can put 2 pi bonds between the carbon and the nitrogen. All right, and so we have our single bond and then our 2 pi bonds. So we added 2 pi bonds. All right, and so your first bond that goes in is a sigma bond. The next bond is a pi, and the next bond is a pi. All right, and so now we subtract 4 for the 2 pi electrons, for the 2 pi bonds. So we have 2 electrons left, and that's what we need on our nitrogen over here. Oh, let me do it this time. All right, good. All right, and so now we have our structure of HCN. All right, so if you have to add 2 pi bonds, sometimes it's 2 double bonds, sometimes it is 1 triple bond. And then they go through all of that. All right, write the Lewis formula for PCl4+. All right, so P is in the same group as nitrogen, group 5. Chlorine is in group 7. 7 times 4 is 28. Now you have a plus charge, so that means you lost an electron, so minus 1 electron. All right, and so when you add those up, you get 32 electrons. So 5 plus 28 minus 1 is 32 electrons. Your central atom is the first atom listed. That is your phosphorus. It is bonded to 4 chlorines. Cl, 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 and Cl. 4 bonds is 8 electrons, so minus 8 electrons for the 4 bonds. Each bond is 2 electrons, 24. And so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 pairs is 24 electrons. That gives us the perfect number to give all of the atoms an octet. So P did not need any electrons. It already had 4 bonds for its octet. Now note that you have a plus charge. All right, just putting a bracket with a plus, that's better than not putting the bracket with the plus. But you need to show which of these atoms actually has the positive charge. So chlorine has 2, 4, 6, 7. Note that we added 7 electrons when we had our chlorine. So each of these chlorines brought in 7 electrons. And that is the correct number of electrons to bring in. So chlorine brought in the 7 electrons. Remember how a covalent bond is formed. 1 electron from the atom P, 1 electron from the atom chlorine. They share and they form that bond. So when you do the charges, it's about the electrons that they brought in. All right, again, all these chlorines brought in the correct 7 electrons, correct for being neutral chlorine. All right, so chlorine said 7. All 4 of these brought in 7. Note that the phosphorus here said 5. The valence electrons for phosphorus is 5. But phosphorus only brought in 4. So the positive charge is on the phosphorus. It was supposed to bring in 5. It only brought in 4 for the 4 that it shared for the 4 bonds. And so it did not bring in its 5th electron. That's why it is a positive charge. And again, they're just going to put the plus charge out here. I want to see that you know that the plus charge is actually right on the P. P brought in 4. It should have brought in 5. It has the positive charge. All right, so now we're going to do Lewis structure. Again, when they have it written as CH3, this is not written as C2H3O2. It is written as CH3. That means that this C has to be bonded to 3 H's. And then it's bonded to this C that is bonded to 2 O's. All right, so we do our valence electrons. 4 plus 3 plus 4 plus 6 plus 6. Carbons in column 4. Hydrogens in column 1. There are 3 of them. Carbons in column 4. Oxygens in column 6. Oxygens in column 6. And we have a negative charge. When we have a negative charge, we need to add another electron. All right, and so that gives us 24 electrons. All right, so then when we draw our skeletal structure, we needed to put in 1, 2, 3, 4, 5, 6 bonds. So that is 12 electrons. That is our 6 bonds that we just wrote in. So we have 12 electrons, and we have to see if that is enough electrons to give everything an octet. And we need 2, 4, 6, 8, 10, 12, 14. 14 electrons required. So we need 14 electrons. We have 12 electrons. That means we need to add 1 pi bond. All right. So when you're adding your pi bond, you're going to add it to here or here. And that's when you have resonance. When you have a choice of here or here, 2 different spots, then you have 2 Lewis structures. When you have 2 or more Lewis structures of the same compound, that's what they are called resonance structures. And so we're going to have our CH3, and then a C, and this time I'm going to put the double bond O up here, and then an O. And then this is the resonance arrow. All right, not to be confused with the equilibrium arrow. This is equilibrium. When we're doing resonance structures, the arrow must have 1 line and a double-headed arrow on each end of that 1 line. All right, and so the other choice is your CH3. And the double bond to this oxygen. So we could put the double bond to the oxygen going up. We could have put the double bond for the oxygen going to the right. And so we have resonance forms. All right, so we have to subtract 2 electrons for the pi bond. So now we have 10 electrons, and that is the perfect number to give everything an octet. 2, 4, 6, 8, 10. Yes. 2, 4, 6, 8, 10. Now everything has an octet. All right, but we do have a negative charge, so we got to figure out where is the negative charge in this compound. H, 1 bond, always 1 bond. That is a neutral H. That's how you will always see it. Carbon should have brought in 4. Carbon will have 4 bonds in almost every single structure. 4 bonds to that carbon. That is a neutral carbon. 4 bonds to this carbon. Yes, that is a neutral carbon. Oxygen brought in 6 electrons. Here's 2, 4, and then 5 and 6. This one has brought in the 6 electrons. This one has brought in 2, 4, 6, and 7 electrons. All right, and so that is the oxygen that has the negative formal charge. And over here, this is the one that brought in 7. This is the oxygen that has the negative formal charge. So oxygen should have brought in 6 electrons, and these oxygens that have a single bond brought in 7 electrons. 6 electrons as your non-bonding electrons, and 1 electron to bond with the carbon here. All right, and so that is your 2 resonance structures. All right, so we're going to talk about a bond order. All right, so when you have a double bond, so we look at this carbon-oxygen double bond, the bond order is equal to 2. When you have a single bond, so bond order 2 for a double bond. Bond order here is 1. All right, so if we look at the same bond over here, this bond that's going up, the CO bond is going up, now the bond order is equal to 1. And the bond order that's going to the right here, this bond order is equal to 2. All right, and so you have resonance. That means it can be in either one. And so we're going to have what's called a resonance hybrid. It just means average. So we're going to take the average, resonance hybrid. So the CH3 is exactly the same in both of them. So we just write CH3. All right, then that's bonded to a C. And then we have an O, and then we have an O. And what we have then is a dotted line that goes between the two, the CO. Because your bond order is not 2, it is not 1, it is the average. So your bond order is 1.5. So your CO bond order is 1.5, or 3/2, or 1 1/2. All right, so you can write it any of those ways. Your bond order is 1.5. The charge of this oxygen, here it has 0 charge, neutral. Here it has a -1 charge. 0 minus 1 divided by 2, -1/2. So each one of these O's is the average is -1/2. So the charge of each one of those oxygens is a -1/2. All right, so anytime you have resonance forms, you are then going to take a resonance hybrid, which is the average. And you will do your bond orders. So again, bond orders are simple. If you have a carbon-carbon single bond, your bond order is 1. If you have a carbon-carbon double bond, bond order is 2. If you had a carbon-carbon triple bond, your bond order is 3. All right, so IF5. So I is in column 7. F also in column 7. All right, and so 7 times 5 is 35. So that's 7, and that's 7 times 5. All right, so you've got your 42 valence electrons. I is the central atom, and it is bonded to 5 Fs. When you put in 5 bonds, you have to subtract the 10 electrons for the 5 bonds. And so 32, you have to see, is 32 enough electrons to give everything an octet? Each one of these Fs needs 6. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, and 30. We need 30. We have 2 extra. All right, when we don't have enough, if we were too short, we'd have to put in a pi bond. This is 2 extra, so remember the rule. When you have extra ones, you simply put them on your central atom. All right, and so there is your Lewis structure for IF5. Note that that is a neutral molecule. So F was supposed to bring in 7. Each one of these Fs brought in 7. I was supposed to bring in 7. How is this 7? Well, it's 1 for each one of these bonds for the F, so that takes 5. And then you have your lone pair, and that is 7. All right, and so all of these are neutral. All right, so that is your Lewis structure for IF5. All right, so then we are going to ask for the number of bonding directions. All right, and we're also going to ask for the number of lone pair directions. And it is called directions because if you had a double bond, that is one direction. So that's two bonds, but they're going in the same direction. All right, so number of directions is important. When they're all single bonds, it's not very important. But when you have double and triple bonds, you might think that a double bond is two bonding directions. No, it is one bonding direction. It's going the same direction. Just happens to be a double bond. But here we have 5 bonding directions. We have 5 bonds all going in a different direction. And we have a lone pair direction. And so then you're going to add those up to get the total number of directions. We have 6 directions. All right, and this is very important to get our geometric arrangement. All right, so geometric arrangement, I will always write GA. That means geometric arrangement. Every time you have 6 directions, your geometric arrangement is going to be octahedral. And again, OH is going to be my abbreviation for octahedral. All right, to draw an octahedral, you would have the I, and then you're going to have wedges and dashes. The wedge means it's coming out at you. The dashes mean it's going back behind the screen. All right, and then we're going to have in the plane and in the plane. All right, so I'm going to put my electron pair at the bottom. That's where I always put it on my octahedral. And then I put in my F's, all 5 of my F's. All right, and so this shape has a square, and then it all goes up to the top here. So this is a square pyramid, so square pyramidal. So your molecular geometry is a square pyramidal. All right, the reason why that's different is that when you're looking at this, your electron pair is invisible. Cannot see the electron pair, so we don't see an octahedral. What we see is a square pyramidal. All right, so when we did CO2, remember we had this structure. All right, and again, carbon with 4 bonds is neutral carbon. Why? Because carbon is in column 4. And so you have your 4 electrons that carbon brought in, and that is exactly how many it should have brought in, and it is neutral. Your oxygen with 2 bonds and 2 lone pairs is neutral. Why? Because oxygen is in column 6, and it brought in 6. Oxygen's in column 6, and it brought in 6. So there are no formal charges for the oxygen or the carbon in CO2. There is, of course, a formula. You can use their formula. I will not be using their formula. All right, so a bond length and a bond order. So we already did this. If I put back up my carbons, and I can have a single bond, a double bond, and a triple bond. All right, so here's the bond order. Bond order is 1. It's the number of bonds between the 2 atoms. Bond order here is 2. Number of bonds between the 2 atoms. Bond order here is 3. Number of bonds between the 2 atoms. Now the length, when we're talking about the length of the bond, when you have 1 bond holding them together, that's going to be the longest. And when you have 3 bonds holding it together, it's going to be held together much tighter, and this is going to be the shortest. All right, so the higher the bond order, the shorter your bond length. All right, so when we look at polypropylene, all right, or simply propylene because they're just showing one of them. All right, so one of these carbon-carbon bonds, this is a double bond. So here is your bond order equal to 2, and here is your bond order equal to 1. All right, so this bond order of 2, this one is stronger and shorter. And bond order 1, that is weaker and longer. All right, so why is it weaker? Well, it's easier to break one thing than it is to break two things. All right, and so when they give you the length and they say one is 150 picometers and one is 134 picometers, well, this one is the shorter one. This is the 134 picometers. This one is longer. This is the 150 picometers. All right, so as long as you know that the bond order that's smaller is going to have a longer bond distance, whatever distance they give you, the longer one, that's the one that you match it up with. All right, so now we're going to find delta H, a little bit different than we did in chapter 6. All right, so we're going to do breaking minus making. So we're going to have delta H, and I just like to do is equal to breaking minus making. Breaking minus making. All right, broken versus formed. I like breaking and making. All right, so it's breaking minus making to find your delta H for these reactions. So you're going to have a chart of bonds, energies. All right, and so you have your reaction. You have to break all the bonds. You have to make all the bonds. All right, so you're going to take your energy for the breaking and subtract your energy for your making, and you will have your delta H. All right, so here we have to identify what are we going to break. All right, so the easiest way to not make any mistakes is to break everything and to make everything. If you take any shortcuts, you can get the wrong answer. All right, note that if we look at a CH single bond, we're going to break 4 of them. So everything on the left, we're going to break. Everything on the left is breaking, and we're going to form this thing on the right. We're going to make everything on the right. So here we're going to break 4 CH bonds. We are also going to break a carbon-carbon double bond. Cl2, you have to draw the Lewis structure. Cl, Cl. We are also going to break a Cl, Cl bond. Over here, what are we going to make? Well, we're going to make 1, 2, 3, 4 CH bonds. We are going to make a carbon-carbon single bond. And we're going to make 2 carbon Cl bonds. All right, so you're going to get your chart. You're going to have an energy for this. It's like 411. You're going to have energy for this. You're going to have energy. You're going to add them all up. You're going to have your breaking energy, and then you're going to take 4 times that number, plus that one, 2 times that number, add them all up. And your delta H is going to be your breaking number, this number added up, minus your making number, this number added up. And that's going to be your delta H for this reaction. And so we just have to find all right, so here's the way they're going to do it. They're going to say that I am not going to add up 4 CH single bonds and break them like I had 4 CH bonds, and then I'm going to make 4 CH bonds because when I subtract those numbers, it comes out to 0. That is fine. I prefer you to break everything and make everything. You've got a calculator, so taking that number times 4 and subtracting that number times 4, you can do that easily on your calculator. A lot of times people will not subtract a carbon-carbon double bond, or they will not put in a carbon-carbon double bond. They will then not put in their carbon-carbon single bond. If you break everything and you make everything, you always get it right. All right, and so here is the breaking for 842 minus the making. I didn't push it enough, 1,000. All right, and so you see that that's going to be a negative 158 kilojoules. So this reaction is exothermic. Your delta H is negative 158 kilojoules. All right, so again, these numbers that you're going to get are going to come right off of a chart that's going to be given on the test. You simply look up those numbers, you add up everything that you're breaking, add up everything you're making, subtract those two numbers, and that is your answer. All right, so that is chapter 9. Chapter 10 is very similar to chapter 9. All right, so this one is going to be doing the octahedral and the square pyramidal that I talked about in chapter 9, but chapter 10 is putting all of these things in 3 dimensions and looking at their molecular geometry as well as the geometric arrangement. All right, so the molecular geometry is the shape of the molecule. Note, when you're doing the molecular geometry, when you're looking at the lone pairs are invisible. So the geometric arrangement, that's when we're going to look at the lone pairs, and then the molecular geometry, what does the molecule look like, because we're looking at it and the lone pairs are invisible. All right, so when we have, I like to call these directions. All right, so I will call these directions. So when I have 2 directions, it is going to be linear. All right, so I have my middle, and then it's going to be linear because the electrons want to get as far apart as possible. And the bond angle for linear is 180. That's as far apart as 2 things can get. When you have 3 directions, all right, and the directions can be bonding directions or lone pair directions. If you have 3 of them, then you are trigonal planar. All right, and so your bond angle for trigonal planar is 120. When you have 4 directions, lone pairs plus bonding directions, you have then tetrahedral. In order to draw a tetrahedral, so this is in 3 dimensions, planar, that's in the plane of the board, linear, that's in the plane. All right, but note that this is not in the plane. If it was 4 and it was planar, it would be square planar. It is not square planar. It is tetrahedral. And so in order to draw a tetrahedral on a 2-dimensional paper, you draw your dashes and wedges. So the dashes, again, that means it is going back, and the wedge means it's coming out. All right, and if it was square or planar, then that's a square and the bond angle is 90. Tetrahedral has a bond angle of 109.5, which is further away than 90, and that's why the electrons will go in this geometry to get as far away as they can from another electron pair, 109.5 degrees. All right, so you have to know the number of directions and the arrangement of the pairs, all right, called the geometric arrangement. So when you have the arrangement, that is the geometric arrangement. All right. When you have 5 directions, all right, so 5 directions, bonding, lone pair directions. You have trigonal bipyramidal. All right, so again, you have to be able to draw this on a 2-dimensional piece of paper. In order to draw this on a 2-dimensional piece of paper, you've got straight up, you've got straight down, you've got straight to the right. Then you have going back, and then you have coming out. And note the bond angles, although they didn't write one of them. All right, so here to here, you've got a 90-degree bond angle, and then you have your trigonal planar around the center. That's why it is a trigonal bipyramidal, and that's 120. But you also have, from top to bottom, you've got a 180. So you have 3 bond angles for trigonal bipyramidal. You got 90, 120, and you've got 180. When you have 6 directions, lone pair directions plus bonding directions, you have the arrangement of an octahedral. Again, you have to be able to draw that on a 2-dimensional piece of paper. And so the center that we're calling A, straight up, straight down, and then you have back, you have out on the left, you have back, and you have out on the right, is how you have to draw an octahedral on a piece of paper. All right. All right, so if you blew up some balloons, they will get as far apart as possible when you tie them together. All right, so that's going to be linear. It's going to be trigonal planar. That's your tetrahedral. Here's your trigonal bipyramidal. Note the 2 different colors here for your trigonal bipyramidal. Just like on Earth, we are going to have the center of the Earth, this ring around the center of the Earth is called the equator. So these are called the equatorial positions, and there are 3 of them. And then, of course, the Earth rotates on its axes. All right, so this is the axial position, axial up, and here's axial down. When you're putting in your electron pairs, they will go in the equatorial positions. The lone pairs will always go in the equatorial positions. All right, if you have lone pairs on any of the others, they're all exactly the same for a tetrahedral, the same for a trigonal planar. When you get to octahedral, you can put your first electron pair anywhere you want. I always put my first electron pair on the bottom. All right, and then you have your square pyramidal. Now, once you have picked a spot, the second lone pair has to go as far apart as possible, which means it would have to go at the opposite end of wherever you put your first lone pair. So for me, I always put my lone pair on the bottom, and then the second one would always go on top. And then now you're a square planar where they're all the same. You pick any one you want, and then the fourth electron pair has to go opposite of that one. All right, so here are all the possibilities. When you're linear, that's it. It's linear. You have 2 directions. And so they give the example of BeF2. All right, so remember here we have our lithium, we have our beryllium, we have our boron, we have carbon, nitrogen, oxygen, fluorine. All right, so that's our second row on the periodic table. So when we have BeF2, note how they're writing this structure. When you have these pretty much never have an octet. These always have an octet. And carbon usually has an octet. All right, so when we look at this beryllium in the center here, well, this beryllium does not have an octet. It only has 2 electrons, which is where it's at on the periodic table. So lithium's in column 1, it has 1 electron. Beryllium is in column 2, it has 2 valence electrons. And your fluorine has 7. And so again, your fluorine, they're not showing the lone pairs on the fluorine. All right, but there are 3 lone pairs, and it brought in 7. It is neutral. It brought in 7. It is neutral. And Be brought in its 2, and it is neutral. All right, so I guess I shouldn't put never. Rarely, / never has an octet. All right, never is kind of strong. You can put an octet there. You would have many, many formal charges. All right, so rarely does it have an octet. Usually it has an octet, but this one is correct as always. All right, so if you ever have a nitrogen, oxygen, or fluorine that does not have an octet, you have the wrong answer. For all of these, the maximum is 8 electrons. If you ever have more than an octet, it is wrong. because for the second row, what you have available is the 2s2 and the 2p6. You have a maximum of 8 electrons that can fit in. You can put in less than 8, but you can never put in more than 8. None of them can have more than 8. All right, so when you do your trigonal planar, all right, so you have your trigonal planar, when you have a lone pair, all right, so this is number of directions, bonding directions. When it's 3 and you have 0 lone pair directions, well, then you're simply your trigonal planar. But when you have 2 of them that are bonding and 1 of them that is a lone pair, that means you can't see this lone pair when you're looking at it. For the geometric arrangement, it is 3. That's your geometric arrangement, 2 plus 1. When you're looking at the molecular geometry, the geometry of it, it is simply bent. All right, so that's what they're calling it there, bent. Note that when you have a trigonal planar, your bond angle is always 120. I'm not worried about less than, greater than. I'm going to stick with the actual predicted bond length or bond angle. And many times it is different than that, but we're going to go with the linear is 180 and your trigonal planar is 120. So your tetrahedral, if you have all 4 bonding or all 4 directions are bonding, you simply have tetrahedral. When you have 3 of them that are bonding and 1 that is a lone pair, and then it's invisible, all right, so then you have a trigonal pyramidal. You have a triangle base that goes up. It's not flat. And so it is a pyramid. It is not trigonal planar. It is trigonal pyramidal. When you have 2 of them that are lone pairs, again, you don't see the lone pairs. You only see the nucleus of the atoms. So you're only going to see these 3, and they are going to be in a bent shape. But note, for tetrahedral, your bond angle is 109.5. So you're going to have a bent that comes from your tetrahedral that has a bond angle of 109.5. You're going to have a bent that comes from your trigonal planar that has a bond angle of 120. So bent does not tell you the bond angle. The bond angle is from your number of directions. Once you have your tetrahedral, you have your bond angle, 109.5. Then you put in your lone pairs to see if you have a trigonal pyramidal or a bent molecular geometry. All right, when we go to 5, all right, so if they are all 5 bonding directions, no lone pair directions, you simply have your trigonal bipyramidal. When you have 1 lone pair and 4 bonding directions, you have to put the lone pairs in the equatorial position. So that's equatorial. That's equatorial. That's equatorial. So we put it into this equatorial. Do not put it in the up-down axial positions. The electron pairs go in the equatorial position. And this one is called a seesaw. So if you make this, you will see that here's the legs of the seesaw. The 2 equatorials are the legs. And then the linear, that is the person that sits on this side and the person that sits on that side. And so it is a seesaw. When you have 2 of them that are lone pairs, again, the lone pairs have to go in the equatorial positions. And so it must go in 2 of the equatorial positions. So now you have the letter T. So it is a T shape. All right. And then if all 3 of your equatorials are lone pairs, then it is simply linear. Now note the bond angle. Linear is 180. T-shaped has 180 and 90. When you are seesaw, you're going to have your 120, your 90, and the 180. Oh, good Lord, I have way more time. Okay, and your trigonal bipyramidal is also 90, 120, and 180. And I did not know I was past time. All right, we will pick up on octahedral next time.